Professor Clements with you as we consider an electric circuit containing a 9-volt battery, wires that are not perfect, that have a total resistance of 2 ohms, and then 3 18-ohm resistors that are connected in parallel. We're going to pretend that the internal resistance of the battery is 0. We want to calculate the current from the battery, the power in the parallel resistors, the power in the 2-ohm wires, and the fraction of the power that is wasted in the wires. Well, our approach to this would be to first draw the circuit diagram. 9 volts, 2-ohm wires, parallel connection of the 18 ohms, and now simplify the circuit. Our first step would be to simplify the parallel arrangement. We use our reciprocal calculation for that. 18 is a common denominator, so there are 3 1/18th terms. 3 over 18, we invert both sides. RP is 6 ohms. We redraw the circuit with the battery, the wire, and the 6-ohm net resistance for the parallel combination. We can calculate the current coming out of the battery, V equals IR, 9-volt battery. The total resistance the battery is facing, 2 ohms and plus 6 ohms, 8 ohms. We get a current of 1.125 amps out of the battery. How much power in the parallel resistors? Well, let's go ahead and use I squared R. We could use IV, but let's use I squared R. We have the current squared, 6 ohms is the net parallel resistance, 7.59 watts in that situation. 7.59 watts from the I squared R calculation. And if I would calculate the potential across the parallel resistance first, then I could use IV. But we have a voltage drop in the wires. So we have 1.125 amps times the 2 ohms for the wires. The net voltage across the parallel combination then is 6.75 volts. And we could calculate the current there. The current being 6.75 volts divided by 18 ohms, that would be in one branch of the parallel arrangement. So I have 0.375 amps in one of those 18 ohm resistors, and a power then of 2.531 watts, doing I squared R in the 18 ohm resistor in the parallel circuit. Since there are 3 resistors, there's going to be 3 times the power. About 7.59 watts would be the power in the parallel combination. If we take a look at the wires, we have the current in the wire, 1.125 amps, square that, 2 ohms for the wire, 2.53 watts in the wire. So less watts in the wire delivered to the wire, heating up the wire, then delivered to the 18 ohm parallel combination. But as a fraction, it's still pretty significant, about 1/3. And 33 roughly percent then would be waste power delivered to the wires rather than to the 18 ohm network, where perhaps that represents some motor or device that we want to deliver power to. It is important to pay attention to the resistance of wires if you're told they have resistance. So keep practicing with that. Again, work on this general principle of reducing the circuit, making combinations of parallel and series where appropriate, and then calculating the current out of the battery, and then work your way back to finish your analysis of the problem. Professor Clements signing off.